Hey there. We're going to use a net force approach to analyzing a system, mass hanging from two chords. First for a simple system where the chords are at equal angles, then for a second system where the chords are at two different angles. We'll start with a system with two equal angles. A sphere of mass m hangs at rest from two chords at equal angles theta is shown. We'll find the magnitude of tension 1. Our process will be to start by stating knowns and unknown variables, draw a free body diagram, use the diagram to write net force equations, and then we'll solve the system of equations we've written. Our knowns are the mass of the object and the angle theta, and the unknown that we want is the tension. We call it tension 1 here. Our free body diagram starts by denoting the particle as a dot in the center. We'll let that be the origin of our system. And then we'll draw in the vector arrows for T1, T2, and mg. We'll include a coordinate system. We'll let y be positive upward, x be positive to the right, and we also will include the angles theta. I'm going to start by finding the net force in the x direction. It equals 0 because there's no acceleration in the x direction. We can define T2 sine theta as the x component of T2. T2 sine theta points to the right, T1 sine theta points to the left, so the net force equals the difference between them. And since the sine theta terms cancel, we get that T2 equals T1. Our tensions are equal to each other. In the y direction, we find the y component of T1 and T2 by taking T1 cosine theta and T2 cosine theta, and then the y component of mg is just the total magnitude mg in the downward direction. We can solve this by setting T2 equal to T1, so that becomes a 2T1 cosine theta equals mg, and just isolating T1, we get the tension equals mg divided by 2 cosine theta. Now we use a similar approach where the angles aren't the same. We've defined an angle alpha and an angle beta, and we want to find both of the tensions in the system. Here I've drawn the free body diagram with the point at the origin and alpha and beta. We'll start by doing the net force in the x direction. Sum of forces x equals 0 because our system is not accelerating, equals tension beta sine beta to the right minus tension alpha sine alpha to the left. Now notice that the magnitude of tension alpha is larger than that of tension beta. That's because alpha is a smaller angle, but they have to have equal x components. That means that the hypotenuse of the alpha angle triangle must be larger than that of the beta. We can set these two equal to each other. T beta sine beta equals T alpha sine alpha. That allows us to solve for tension beta equals tension alpha times sine alpha over sine beta. Now let's do the net force in the y direction. We define T alpha cosine alpha as the adjacent to the angle alpha, and T beta cosine beta as the adjacent to the angle beta. For net force in the y direction, it equals 0 equals T alpha cosine alpha plus T beta cosine beta minus mg, which points downward. Notice this time, T alpha cosine alpha is not equal to T beta cosine beta, but they add up to equal mg. We can use substitution here. Our T beta equals T alpha sine alpha over sine beta. We can substitute that into our equation. So now we have an equation all in terms of T alpha and knowns. We can simplify our equation a little bit by noting that cosine beta over sine beta is 1 over tangent beta. And then we can solve for T alpha. It's just mg over cosine alpha plus sine alpha over tangent beta. We can find the tension T beta by going back to our earlier form and substituting in our expression for T alpha. So to recap, we did a force analysis on two different systems with masses hanging from two cords, one with cords at equal angles, one with cords at different angles. We used the same procedure both times. Started with a problem statement. We defined our knowns and our unknowns. We drew a free body diagram. We used the diagram to write net force equations and then solve those systems of equations for tension in each case. Thank you for coming. Come again soon.